Well, hello again, my students. This is Mr. D coming at you with another math instruction video, another session of math, another daily dose of math, sorry. Uh, so we've just started on the unit on linear relations. So it's in grades 7 and 8, it used to be called linear patterns, but its name has changed. It's an upgrade to linear relations now. But I will start it off exactly the same way as they teach it to you in grade 8. So here are the objectives that we're trying to go after here, or trying to get you to learn, or I'm trying to teach you. This is linear relations. So the objectives are, well, being able to recognize linear relations from diagrams. That's what this one's going to be about, this video. And as you know, in class, if you were in my class, your real objective really throughout the unit is be able to recognize linear relations from diagrams, from data tables, from graphs, and from real life examples. So I don't know if we're going to be able to do the real life example of a linear relations here today, but we'll try to maybe in the next video as an example. So here's one. Next objective is to be able to create a data table. Okay, so I'll show you how to do that. That should be pretty easy. Be able to describe linear relations. So I've shown a linear relations to LR, so that's what linear relations stands for now. And finally, this one here is probably the most important part of this first lesson, is being able to determine algebraic equations of linear relations. Okay. And finally, if you did determine the algebraic equation, that's verified and see prove that if it works for the entire data set, and be able to use that algebraic equation to answer questions, of course. Okay, so let's begin with an example. So here I drew an example of what might be a linear pattern, and I guess first question is, how do you know this is a linear pattern if it is? Well, in class, a linear pattern is one that actually has a constant change. But if it relates to things, in this case, a figure number, and here we are counting actually the number of squares, okay? So if there's a constant change in one variable, that is the figure numbers, and a constant change in the other, in this case, the number of squares, then this is a linear relation, okay? And, you know, as compared to things that are nonlinear, well, maybe I'll give you an example of that a little later. But in class, yeah, we've talked about what linear relation is. So this one really is an example of a linear relation, okay? So from this pattern, from this relation, I think we should be able to create a data table, okay? But to prove that this is a linear relation, well, let's just count the squares then. 1, 2, 3 here in figure 1. 1, 2, 3, 4, 5. So from here to there is an increase of 2. If the next one is an increase of 2, then this definitely is a linear pattern. So let's see, 1, 2, 3, 4, 5, 6, 7, 3 to 5 to 7. That definitely is a constant increase of 2. Okay, so this is definitely a linear pattern. And so when you get a linear pattern like this, then our next step could be to make a data table for it. Okay. Again, still pretty much a grade 8 review. So let's make a data table. I think we'll put the figure number here because usually this is where the they put the figure number, which is in this case, I'll mention to you what an independent variable is. Okay, and let's give that a letter F. And of course, the dependent variable is the number of squares. That's the one that's changing dramatically. Number of squares in this side of the table, and we'll give that a capital S. Okay, So let's fill out this data table. In figure number 1, we did count how many? We counted 3. In figure number 2, we counted 5. Figure number 3, we counted 7. Now, if I was to ask you to draw figure number 4 and figure number 5, would you be able to do it? Well, I hope you can, because it really is just, as you can see, increasing only by 2. So if we were to draw figure number 4 and figure number 5, figure number 4 would probably have 9 squares, and figure number 5 would probably have 11. Okay, so there's your data table as far as figures go, starting with 3 squares and constantly increasing by 2, so we're counting. Okay, and so notice that is what's happening in our data table, and this is what makes a relation. As one is constantly changing, the other variable is also constantly changing. In other words, by a constant amount. Okay, in other words, if this was increasing by 2 and then by 4 and then by 6, or different numbers every time, then this is no longer linear. Okay. So there's your data table. You create a data table. Okay. So now let's give this a description. When I ask for my students to describe this, I want them to just keep it very simple. Okay. When I ask you to describe it, let's just keep it very simple and just describe what's happening to one variable and describe what's happening to the other variable, such as this. And advisably, this is the easiest way to describe a linear pattern. Okay, as figure number increases by 1, comma, the number of squares increase by 2. Oops. And that's it. That's the only description I'd really want. Okay. Keep it simple, keep it straightforward. Okay. Next, now we actually have to determine the algebraic equation for this. Well, how do you know which letter to use as the equation? Well, is this really about the number of squares, or is it about the figure number? Well, this really is about the number of squares, because that, for one thing, according to our diagram, that's the one that's really changing dramatically. Whereas the figure number, well, that's just counting by 1, and that's really just labeling what the diagrams are, or counting them. So as far as these two variables are concerned, figure number and number of squares, the number of squares really is what they would call the, I'll put it down here, called the dependent variable. And the figure number is the independent variable because it acts independent, okay, of the other variable. It's independent of what's happening with the number of squares. Another way to explain dependent and independent variable in this case is, if somebody asks you, well, how many squares do we have here? Well, then the answer would actually have to be, that depends, the number of squares depends on which figure number you're talking about. And that's why it's the easiest way to call it the dependent variable. How many squares you have depends on which figure number you're talking about. Okay? So that being the dependent variable, therefore that's what the equation is about. S equals. Now, what is S equals something? Okay? So in general, S equals, the equation for this is going to have something multiplied by the figure number, and maybe plus or minus an adjuster, I call it. Okay? Or a constant. So what is this number that's going to multiply the figure number? Well, it's really this number right here. Whatever this constant increase is, I tell my students that is what multiplies the figure number immediately. Okay? Okay. And now to get this adjuster, well, you're just going to have to test it out with one of these data sets. Well, I usually like to tell them, try it out with the first one. If you try it with figure number 1, if f is equal to 1, what is 2 times 1? Well, that's 2. Well, how do you make a 2 into a 3? Well, we have to add 1. And so this is your equation. S equals 2 times f plus 1. Okay, so if you didn't get it right away from my first explanation, you can just reverse this video, I guess, and listen to it again. Again, whatever this increase is, that's the number that multiplies the figure number right away, this variable, the other variable. And then to find out what your constant is, or the adjuster, well, you just substitute this figure number 1 into this temporary equation. You get your 2 times 1, and then to determine 2, what do you have to do to 2 to make a 3? You have to add 1. And this is your equation. Okay, and this is why we verify also. Okay, if in fact this is the equation, then it should work with any of these data sets. If figure number 3, is plugged into this equation, we should get 7 squares. Okay, so better yet, okay, so let's prove it. Here's how you verify. Write out the equation. And by the way, if I remove the multiplication here and it just butted together, this still means a multiplication. Let's test it out with data set number 3. If figure number is 3, so substituting the 3 here, does this equation actually equal to 7? Okay, well, let's find out. 2 times 3 is 6. 6 plus 1 is 7. So there's your verify. This is what proves that this is, in fact, the equation for this linear relation. And now that we've done that, we can actually use this algebraic equation to answer other questions, such as which figure number has, oh, hold on a second. Let me do the other one first. How many squares? Let me do this question first. How many squares, is easier, how many squares are in figure number 21? Now, obviously, you're not going to try to draw 21 figures or, and then count the number of squares. Obviously, we're going to use our equation, S equals 2f plus 1. Simply substitute the figure number now 21 into this equation. And do our math. 2 times 21 is 42, plus 1 is 43. Okay, so there are 43 squares in figure number 21. We can also ask this question. I'm going to try to squeeze this in this little space here. Which figure number has, I don't know, has 61 squares? Okay, and so now the substitution starts with S equals 2f plus 1. It's 61 squares here, and then 2f plus 1 here. And this is a little review of solving equations. Then you subtract 1 on both sides. We'll get you 60 equals 2f. Finally, divide both sides by 2. And f equals 30. So figure number 30 has 61 squares. I hope this helps. So there's more videos coming, and on other things, like maybe helping you out on how to do some of these assignments. So I hope this helps. Thank you so much, and bye-bye for now.